Hello everybody, welcome to your Lecture 13 skill check on two-way ANOVA. So what do you need to be able to do on the final exam for this topic? Given a scenario and Minitab output, you need to be able to identify the factors and factor levels, and then to conduct a two-way ANOVA in 3 steps. So first, you need to be able to confirm that all conditions are satisfied. Equal variance within groups, nearly normal residuals, no interactions between factors. And then you need to understand how to identify factors that are significant, and if necessary, follow with multiple comparisons to find out which levels of those factors are making a difference, and then to draw a conclusion. So let's look at all of that. For this scenario, here we're imagining that a company manufactures light bulbs and that it has factories in 3 locations. And so location is going to be one of our categorical variables. Each factory manufactures light bulbs with 4 levels of power, and so that's going to be a second categorical variable. We're imagining that on the first day of each month, the head engineer of the company, Dr. Haragwe, collects a random sample of 9 light bulbs of each type from each factory for a total of 180 bulbs. She then gets her staff to measure how long it takes for each light bulb to burn out. So we have a sample size, and we have our quantitative predictor variable, which is the time it takes for a light bulb to burn out. And so we're imagining that it is well known that light bulbs with greater power tend to have shorter lifetimes. So Dr. Haragwe is mainly interested in differences between factories, and specifically she wants to be sure that all 3 factories are producing light bulbs of equal quality, which means they have the same time before burnout. And so here we're pretending that you have been hired to analyze Dr. Haragwe's data and to report to her the appropriate conclusions. So one way to sort of visualize the way this experiment has been put together is to make a table like you're seeing here. So one of the categorical variables, the location, is on one side, and then along the top we have the power, and you can see that we're drawing samples from 12 different populations. 9 light bulbs each, and then 9 times 12 is 108 light bulbs in total. Right, so the first question is to identify the factors, factor levels, and the response, and to say something about what the populations are. So the predictor 1 is factory location with 3 levels. Predictor 2 is power with 4 levels. And the response variable is the lifetime before burnout. Each combination of factory and power represents a different population of light bulbs, and so there are 12 populations in total in this scenario. Before continuing, I want to say something about terminology. Mainly because sometimes it's a bit confusing. So you'll probably recall from class that I define a factor to be a variable that is controlled by the investigators. And so the classic scenario is, say you're going to test a new drug. You get some volunteers or some patients. You select them at random, divide them into 2 groups. One group gets a placebo, the other group gets the drug. In that scenario, you control who gets the placebo and who gets the drug, and so we call that a factor. If there are more than 1 factors, then we can also talk about various treatments. A treatment is a combination of factor levels. Now, the point of this is in the current scenario, factory location and light bulb power are not controlled. Right? We're selecting light bulbs at random from various factories, and we're selecting light bulbs of various kinds, but we don't control which light bulbs are, let's say, 15 watts, which light bulbs are manufactured in Sackville. We have no control over that. Those labels are already attached to the light bulbs. So in a similar way, if going back to the clinical setting, if we have 2 groups and we assign one group a placebo and the other group some dosage of a drug, some of those people are smokers, some are non-smokers. We don't control who smokes or doesn't smoke. those labels are already attached to the individual people, right? So that's the difference. And so to make that distinction, I'm going to call factory location and light bulb power, I'm going to call them predictor categorical variables, or simply just predictors. And again, the purpose is just to make it clear in our mind the difference between factor levels that we can control and factor levels that we do not control. So having said that, let's continue. So here we're going to explain why we can assume the independence assumption is satisfied in this scenario. And so certainly we can assume that light bulbs in the same sample or group are independent because they were selected at random. That's the whole purpose of randomization, is to guarantee or at least increase the probability that we're getting individual measurements that are independent of each other. We can also assume that the 12 samples are independent of each other, and the reason is each sample was drawn from a completely different population. So here we can assume that there's independence. Next, we do the visualization step. And so first, we're looking at a visualization of the spread and the central tendency of each of our 12 samples. And so in this plot, we have kilo hours on the vertical axis. So for example, 5.0 represents 5,000 hours before burnout. Down on the bottom, we have our two predictor variables, location and power level. So clearly, looking at this data, clearly we can see that there are differences in central tendency. In terms of spread, we could also say that the spread of each of these samples, they're approximately the same. And how do we test that? Well, we look at the range from the top whisker to the bottom, or we can look at the interquartile range. There are differences, but they are fairly small, and so we can say there's probably going to be no reason to suspect that these populations have different standard deviations. Of course, we have to do a formal test, but visualizing the data helps you to anticipate what you can expect to see when you do the formal analysis. And so here we can see the range and the interquartile range for the 12 samples are roughly similar. And so the 12 populations from which the samples were drawn might have the same spread, or in other words, the same population standard deviations. The sample medians are not all the same, and so the 12 populations from which the samples were drawn may have different central tendencies or population means. So again, the purpose of this stage in the analysis is to anticipate what you might expect to see when you do the formal analysis. It also helps you to identify problems. So for example, if you might notice some outliers, or you might notice that one group maybe has a really big spread compared to the others. Okay, so the other part of the visual analysis is to look at the interaction plot. So here we have our interaction plots. Vertical axis again is the mean. The mean is in kilo hours. So again, 5.0 represents 5,000 hours. We have power along the bottom, and the color coding is for the different factories. So there's several things you can notice from this plot, but the most important thing is to check for interactions. So again, we have one plot for each factory, right? These are color coded, and these plots are parallel with only slight deviations. It therefore appears that the two predictors, factory and power, do not interact. So this is the main thing you're looking at when you examine the interaction plot. Note also that the sample means for the Sackville factory appear to be systematically less than the sample means for the Halifax factory. And what I mean by systematic is each of these red mean values for Halifax is bigger than each of these green values for Sackville. So that difference is the same for all levels of power. It seems to be systematic. And so we might suspect that when we do the analysis of variance, that we will identify an effect due to the different factories. So in other words, we might identify this predictor variable, location, as being something that makes a real difference. Right, so that's the visual component of the analysis, and now we can turn to the more formal statistical tests. So first, we want to test for equal variances or equal standard deviations across these 12 populations. And so this is some typical output that you might see. The null hypothesis in this scenario is that all populations have the same standard deviation. Here we can see that the p-value for the test is very large, and so we cannot reject the null hypothesis at any reasonable level of significance. And so what can we conclude? We conclude that there's no evidence that the 12 populations have different standard deviations. So what that means is differences in individual light bulbs, those differences are going to have a spread that is the same for all populations. Now, let's suppose you weren't shown the p-value for the test. How else could you tell that the populations probably have the same standard deviations? Well, you just have to remember that each blue line here is a confidence interval for a population standard deviation. And we fail to reject the null hypothesis if it is possible to draw a vertical line that passes through all of these confidence intervals at the same time. Here, that is clearly the case. And so just by visual inspection, we can tell that there is no reason to think that some of these populations have different standard deviations due to individual differences compared to others. Next step is we want to check for normality of the residuals. So here is the residual plot. Often these two plots are given together, but to check normality, you only need to look at the normal probability plot. So in this case, looking at that plot, most of the markers are lined up like beads on a string. In other words, in a straight line. So the residuals, we can say, are approximately normal in distribution. We do note, however, that there is one unusually large residual, and that residual is evident in both of these plots. And how do we know it's unusual? Well, for one thing, it's far away from the rest of the residuals, so that's one thing. But the sort of best way to check is to first realize that these are standardized residuals, and so most of them should be between plus and minus 2 standard deviations of 0. This residual is nearly 4 standard deviations away from 0. Now we know if the distribution of the residuals is normal, virtually all of them are going to be no more than 3 standard deviations away from 0. And so 4 standard deviations, highly unusual. What do we do about this data point? Well, it could have been just a bad sample. Maybe there was some fatal defect in that particular light bulb. Or maybe it was actually better, because being 4 standard deviations away on the positive side is telling us that this light bulb, its lifetime was much more than average. So actually that light bulb was better than most. How do we explain it? We don't know. We'd have to go back and look at that individual light bulb to see what's going on. Does it matter for the analysis? Not really. It does have an impact, but the impact is not really important. And what impact does this one residual have? Well, it is this residual that makes this interval for the population standard deviation so large, right? So it is this large residual that explains why the interval estimate for the standard deviation of this population, Halifax 120 watt, is so wide. If we took that residual away, took that observation away, this interval would have a width that's more comparable to the rest of them. As far as I can tell, that's the only impact this residual has on the analysis, so there's no reason not to just leave it in there. Okay, finally, we need to look at the analysis of variance table to see if there's evidence that the two factors, or what I should say, the two predictor variables interact, right? We have two predictors, factory and power. We have an interaction term here in the table, and all we need to do is look at the p-value for that interaction term to draw our conclusion. So remember that the null hypothesis is that there is no interaction between these two predictors. This null is not rejected because the p-value of the test is greater than 5%, assuming a 5% test. So we can conclude that there's no evidence to suggest that the predictors, factory, and power interact. This shouldn't come as a surprise because when we looked at the interaction plot, we saw the plots for those three factories were roughly parallel to each other. So this is not a surprise. This is what we expected to see, in fact. Now, at this point, we have shown that all of the conditions for two-way ANOVA have been satisfied. In particular, we have the condition that each population has the same standard deviation, that the residuals are approximately normal in distribution, and that there are no interactions between our two predictor variables. And so now we can proceed with the analysis to try to answer the question that was originally asked, which is, does factory make a difference? And so we look at this first row of the table, and we'll notice that looking at this row, the null hypothesis that the population mean is the same for all factories is rejected because the p-value of the test is so small. Hence, there is very strong evidence that the population mean lifetime is not the same for all three factory locations. Now, of course, you'll also notice that the p-value for power is very small, and this is consistent with the prior understanding that light bulbs with greater power tend to have shorter lifetimes before burnout. And so this second line of the table is confirming what in this scenario was already known. The first line is giving us information with respect to the question that was originally asked. Does the factory make a difference? Here we can say it does. Now, since the factory makes a difference, we now want to know in which factory is the quality of the light bulb on average less. And so to do that, we turn to multiple comparisons. And so here is our multiple comparison table. We have two ways to conduct the analysis using this table. We can either look at confidence intervals, or we can look at the p-values. So the thing to remember here is that each row in the table corresponds to a two-sample t-test. The null hypothesis in each case is that the population mean lifetime is the same for both populations being compared. So for example, in this first row, we're comparing the mean lifetime for light bulbs made in Halifax compared to Dartmouth. We notice that this interval contains 0, and so we can therefore not conclude that those population means are different. The p-value is also quite a bit larger than 5%. And so for all of these comparisons, the null is rejected if the confidence interval for the difference between population means does not contain 0, or equivalently, if the p-value for the test is less than the significance, the level of significance of the test. So we have two ways of making our comparisons. And so in this case, we can say that the values in this table indicate that the population mean lifetime for light bulbs made in Sackville is less than that for both Halifax and Dartmouth. And how do you tell? Because these intervals are both negative. By comparison, the population mean lifetime is the same for Halifax compared to Dartmouth. Now, in the final exam, when it comes to this kind of question, you might be given a table as we just looked at, or you might be given a diagram like this one. And so here you can make the same conclusions simply by visual inspection. So you can see a comparison of the mean response for Halifax versus Dartmouth. That interval contains 0, so there's no reason to reject the null hypothesis. For Sackville and Dartmouth, both of these intervals, for Sackville versus Dartmouth and Sackville versus Halifax, both of these intervals are negative, which is an indication that the population mean response for Sackville is significantly less than the population mean for both Dartmouth and Halifax. So the same conclusions are being drawn as as with the table on the previous slide. And so finally, we want to make some conclusions. So first, we can say that all the conditions for the two-way ANOVA were shown to be satisfied. In particular, the standard deviation was determined to be the same for all populations. The residuals approximately normal in distribution, and there was no evidence of an interaction between the two predictor variables, factory location and light bulb power. And so what all that says is we can put trust in our final conclusion. For the final conclusion, concerning the question, do all three factories produce light bulbs of equal quality, there is strong evidence that the population mean for the Sackville factory is less than that for the Halifax and Dartmouth factories. Right, so hopefully you can see how this kind of analysis can be very useful. So even though this was an imaginary scenario, it's not unrealistic. So Dr. Haragwe would be very interested to know that the quality of light bulbs being produced in the Sackville factory are less than those being produced in both Halifax and Dartmouth. And so what she could do is take her team of engineers to Sackville and try to figure out what is going on, what is different between that factory and the other two, and then make adjustments to improve the quality of her product. Hopefully you found this useful. Thanks for watching. I'll see you next time.